Okay, let's start. Good afternoon, everyone. Thank you very much for attending this online technology meeting on display for virtual reality application. I'm Jeremy Picot-Clemente. I'm technology specialist at EPIC, and I'm very pleased to welcome you here and to moderate this online meeting on this topic. So a few words about EPIC before to start. So EPIC is the largest industrial network in the world in the field of photonics. We have today more than 800 members. We cover all the value chain of the photonics industry, from the component manufacturer to the design and prototyping company. And we include also users and system integrators, of course. We also cover all the photonics application, which is quite wide, as you may already know. So from space to defense, including medical, quantum, AR, VR, of course, agriculture, etc. So how we support the photonics industry? We offer a large panel of services to EPIC members. So technology support, market and technology report, networking opportunities, access to market, US, Asia, mentorship, HR support with a website, jobs in photonics, and also investment support for companies. Here is the EPIC team. So I'm personally a part of the technology team with my colleague Antonio Castello and Ivan Nikitsky. So Antonio is in charge of biomedical and laser technology. Ivan is in charge of quantum and integrated photonics. And I'm personally in charge of optics, optical system, and AR, VR, of course. Few words also about the next event we'll organize. So as you may already know, we organize in-person meeting and online meetings. For in-person meetings, we will organize something in Munich these days. We'll be also in France talking about a medical market. We'll be, of course, at Photonic West end of January. And then we'll also cover some defense topics at Optro, but also at Exosense in March. And EPIC is organizing next year its AGM in Juan-les-Pins, south of France, close to Nice. And about online meetings, we'll talk in December about space topics, lasers topics, and in January about data centers. And then beginning of the next year, photonics for cultural heritage. And we will also cover some HR topics with our team, talking about expanding the talent pool beyond photonics. Few words also about the attendees of today's event. So as I said, we cover all the value chain. We will have today some integrators, materials manufacturers, metrology and testing companies, software, research and development, also centers, and also component and modules companies. So we cover all the value chain, and you can find people from all these companies today, at least they're registered for the event. And yes, few words also about the agenda of today's event. First, I would like to thank our speakers for accepting the invitation and talking about this interesting topic. And I would like also to thank our sponsor of today's event, PHIX, which is a company which provides scalable assembly and packaging services for photonics integrated circuits and optoelectronics modules. So we'll start in a few minutes with Jan Hendy, CEO at Hendy Consulting. You will talk about the market and also the technology. We'll have a presentation from Uwe Wogel from Fraunhofer IPMS. You will talk about high resolution display for near to high virtual screens. We'll continue with Gareth Jones from IQE, sorry, and you will cover micro-LED epi wafer topics. Then Stan Larocque from Lynx Mixed Reality. We will talk about display and optics for MR. Tobias Sorg from Ensolt and you will talk, Tobias, about visual precision drive XR immersion. And we will end this meeting with a nice presentation from Bert Wistoller from Fluxim. You will talk about enabling tools for research in emerging display. So thank you very much again for attending this event, and thanks to all of our speakers. And now I would like to start with our first speakers of the day, Jan Hendy from Hendy Consulting. So Jan, I will stop sharing my screen. I will let you start. Thank you very much.
And everybody will have to tell me now, do we have the front page?
Good.
Okay, good afternoon, everybody. I'm Ian Hendy from Hendy Consulting. My business has been around for about 20 years, advising clients across the whole display industry, materials companies, equipment providers, novel display effect makers, and the display makers themselves. So I've covered a very large portion of the display industry in different ways. And very nicely, about 6 to 9 months ago, Epic asked me to write a complete market report on AR, VR, but with an unusual cross-section. So the cross-section was to take displays all the way through then to the optics and waveguides for both AR and VR. And so if you're an Epic member already, that report is already available to you and you can go have a look at it. I'm told today the focus from Jeremy is VR. So what we have here is a small selection of market context slides, mostly around VR, although I will provide a little bit of commentary since I know people like Gareth from IQE will be talking about microLED. That's more of an AR play, so maybe we can put in a little bit more of commentary on the AR space, because I'm sure everybody's very excited by Meta Ray-Ban's display at the moment and the beginning use in much higher volumes of wave-guided technology in AR. So I'll try and talk a little bit to that, but mostly the focus is VR. This then is a small portion of the total report you can get if you're an Epic member, so please go and find it otherwise. So just to set the scene for me, what I'm defining as VR is basically a completely captive visual system, even if there are cameras on the front of the headset that then passes an image inside. So the Apple Vision Pro probably would be more like VR in this translation. You've got then a completely closed system, and that tends to then lead to a narrower set of the display technologies that we'll be talking about. You're not competing with ambient light in the same way that you are in AR. So you can basically say the display requirements and the display technologies that come up are actually different across the two here. So while we'll talk a little bit about those that are in AR because it's sexy and hot, the focus really for me for most of this presentation is the VR piece. And if you look historically, and thanks to the people at Counterpoint for most of the historical data, I basically see VR as a sort of roller coaster between 6 and 10 million units a year. If you can see it here, it's mostly a computing centric application, a lot of it for gaming. People wear, young men and women wear it for gaming and use at home. That is where it's been. So one conservative outlook on the world is that it never gets out of that range, but you're talking less than 10 million units total. Now, this overall picture also adds on it, and just to talk a little bit about that, the true AR headset marketplace, which I see as a B2B marketplace mostly, where you're doing heavy overlay of computer information on the user. And then the new trend, which has really started between Meta and Ray-Ban of smart glasses. Those are shown there in green, and actually up till 2025 didn't really have a display in them. They were first-person viewer glasses for use for out and about influencers, but that marketplace is the one that's now growing relatively well. There's a very strong product launch by Meta, and those are beginning to include a small single LCOS display from Omnivision. So that's been in the press recently. If you translate that then same historical picture to an outlook on value, you're talking about a $4 billion business. So at hardware value for the displays here. So I guess if you translated that against smartphone, which would be 40 billion, you're talking about a very small portion in comparison. But the average headset price is about $500, and actually this is the total hardware value for the headset. The two marketplaces, AR and VR, are distinctly different in terms of their level of fragmentation, and also in terms of their total scale. This is actually taking a 6-year view of AR and VR, and as you can see, VR is substantially larger, and even within that, Meta absolutely dominates. And other than that, Sony plays a smaller role here, but then the dark blue slice is others, so somewhat fragmented. If you turn to the AR marketplace, it is actually dominated by the Chinese at the moment, and is actually a very, very large number of very small slices within what people talk about as AR. Now, if we go down a level, and I don't know that these are provably true, there's a lot of web searches behind all of these, but it's trying to actually look at the cross section, which is the display provider and the optics across a number of top 10 products. And as you can see there, the top 6 in yellow are VR devices. And so predominantly LCDs are the winner in VR devices so far, broadly available for a number of players. Actually, the leading suppliers at the moment are the Japanese, so JDI and Sharp, but BOE and China Star have also expressed interest to want to be in that business. And my forward-looking outlook is basically that LCD will remain dominant within that space. Now, other parts that get discussed are the AMOLEDs on silicon, which is the way that Apple went from Sony Semiconductor. And then there's been some rumors that there's been some discussion that AMOLEDs on glass will also get used in the new Apple Vision Pros. So they're slightly cheaper. Clearly, that's a different value proposition than working on CMOS silicon, working on glass. But it's the competition of those 3 display technologies. Now, largely the optics, and I thank Andreas Giorgio, who worked with me on this report, the dominant one you can see looking forward are pancake optics, and the older versions were slightly cheaper with the Fresnels and the hybrids, and you can see the role of some of the very large Chinese integrators. Gertech is particularly important for some of the optics overall in the VR value chain. And so a typical, just to look here at the Meta Quest 3, a typical setup would be dual 2.5-inch LCDs based on low temp polyoxide with about 1200 PPI. So, I mean, to get to those sort of levels, you are talking about specialist technology from a display point of view. You've got very, very small aperture ratios. Typically, you want very fast switching liquid crystal and very high refresh rates. So I think Uwe is going to talk a lot more about the display requirements, and I think this will dovetail quite nicely. But these VR displays based on LCD are not that straightforward. They are actually quite challenging from a technology perspective, and hence the role of the Japanese suppliers up to now in this marketplace. So a little bit of a recap, and this is the 3 cross sections again. I mean, broadly, you can see this is a $3.5 to $4 billion hardware industry of about, call it cycle adjusted 7 million units a year, with Meta very strong. And then LCDs being dominant at about 65% of the total. And then there's actually a shift going on within the optics, moving from Fresnels to pancakes, which are more efficient, more expensive, more complex, but more efficient with light. And so then the question becomes, and this is where forecasters love producing wonderful hockey sticks, what will be the future here? And so we're really staying only within VR. You know, the bearish outlook is really that this stays in a prolonged winter at less than 10 million units a year, and that carries on that way. And frankly, sometimes I have some of the belief in that. You have to look for what are going to be the true change events that make VR substantially different and cause it to grow. However, the sort of general belief of the marketplace, backed by IDC, TrendForce, and others, is a sort of $20 to $30 million headsets mark by 2030. So it is for some quite pretty reasonable growth. But then I have seen, again, some people who are going for the crazy end of the scale at really, really much higher portions than that. So as you can see, it's about 6 to 7 to 8 million now, going to a range of predictions from a number of players that is actually very big. And I guess if I had to give my general outlook, as I'm a little more bearish on the lower end of this than the total. So the forecast we ended up putting into the report again is for around the 7 to 8 now, growing to the 20 to 30 million range, just to fit with sort of the consensus view of a number of market analysts. And recapping again, when we're talking about VR product, by far the dominant technology, and about 2/3 of the volume is specialist liquid crystal displays. There is some OLED on silicon and some OLED on glass. Now, I know in later discussions, Gareth and others may be talking about AR, and then in AR you've got again the role of AMOLED on silicon, but then liquid crystal on silicon, which is a very old display technology, has been around a very long time, but was actually the one that Meta has been recently using in their Ray-Bans display. And then the microLEDs. And basically, I think the general thesis is the microLEDs will win based on their product attributes: very, very high peak brightness, the ability to go to small pixel size over size, very linear light output is capable for coupling into waveguides. There is a general view that microLEDs are going to be a very good thing. However, today there's really only one dominant market supplier, which is Jadebird. And so this one, I think, will be better handled by a Mr. Uwe that follows later. But it's basically then what are then the display aspirations. And I think Goertek has done some wonderful stuff in the public domain on where the future wants to be. And in general, we'd like to be at more than 60 pixels per degree at reasonably high frame rate. Pretty bright to the eye, but though this is a completely closed system, so it's not the same as the AR environment. And then how is that being delivered is down here on the bottom right. Here is actually at the moment a mixture of LCDs, which are basically mini LED lit, right? They're very bright LCDs with fast liquid crystals and high refresh rates against the micro OLEDs on silicon, which are at a much higher price point. And I think people know there are a range of product launches still within the VR space, so it's definitely not game over in that space. I think a lot of more of the excitement is in AR today, but there are a number of VR product launches coming through over the next 2 or 3 years. One of the real strengths of the market report is some quite detailed company profiling of, I think, more than 50 companies across AR and VR. And I think that's something that I've always been fascinated with, is who's working with whom and why. Where are these important players distributed across the world? And what does that mean for who will win and why? And just one of my always concerns is that, particularly for AR, though not shown here, there is a very, very strong Chinese ecosystem today. And I think there's a lot of named players in China that I think people should focus on more than they do. I think people tend to see AR, VR as being a Western brand, right? Like a Meta or Apple driven marketplace. And actually there's going to be quite a lot of government support and interest from Chinese companies that sit behind all of this. So we should be a little bit careful. We're going to do a little bit on displays, a little bit on optics, and then I think I'm done. So the VR space really is the 3 market display technologies that compete so far. As I've talked about, sort of mini LED lit, quite bright, fairly small pixel, unusual liquid crystals so that they switch very quickly, high resolution LCDs, right? That's the dominant volume. And JDI and Sharp were the first ones in. Not surprising, it's niche business and high capability. But I think as soon as the people like industry leader BOE and China Star, which is the Chinese number 2, pile into this place, you'll see heavy cost reduction, price reduction. This will, even though these are difficult displays, I think the prices of these will go down quite a lot. Then competing with OLEDs on glass, which so far has been really dominated by SDC, and AMOLED on silicon, where Sony Semiconductor was the winning player and actually has got a very strong position in AMOLED on silicon. And then if you look at this here and now, this is headset numbers. I think in the report there's also display numbers, display revenue, but this is done by numbers of headsets. The view that Andreas and I took was for supply reasons, for cost reasons, for market focus, because even for SDC, the AMOLED on glass is the business for headsets would be a tiny portion. Their main focus over the next 10 years is actually OLED IT panels. So if you start thinking about the big picture on the display industry, it's much more likely that LCD will remain really strongly dominant in all of this. And so the players we're talking about are the two Japanese so far have the VR supply, but then when you move across to AMOLED and glass, that's SDC in Korea, and the AMOLED on silicon would be Sony Semiconductor. Looking a little bit, and my friend Andreas is not here to give his detail on this, but VR optics are basically a move from Fresnels initially, which were pretty cheap and gave a reasonable image, although some imaged artifacts, moving towards then now a mixture of hybrids and pancake lenses. And the general view we had here was this will move fairly quickly and heavily towards pancake lenses. They're more complex and sophisticated, typically in the $8 to $15 a piece for each eye range. 4 major suppliers across this, so it's a consolidated industry for optics. But that's probably where VR is going to move. And so that again here was the outlook here, pancake lenses being the important one, and with some hybrids in the market mix as well. As I said, the optics industry is actually pretty consolidated, with Largan, Sunny, Young Optics, and GSEO being the dominant players, Largan in particular being very big. So some of the technical and challenges of producing these lenses at the price points they need to be tend to restrict this to a fairly small outlook of players. And I guess one thing we always wanted to leave Epic with was what are the unsolved, unmet needs still in the displays and optics. And I think there's still more emphasis on increasing frame rate, increasing resolution, everything at lower cost, because again, how do you move the needle on VR headsets if the average headset price is about $500? Part of the answer of that is to move these to much lower levels. Improvement then in the field of view and pixels per degree, and improvements in the form factor. So that's a mixture of new materials and multiple elements for optics. And so that's me. I think I'm done. The main focus I wanted to bring just at the beginning was mainly VR. We're talking about a sub 10 million units a year marketplace today, with hardware value of a little below $5 billion. That's the total hardware value. There is a big question about how fast this grows. It's basically a computing and gaming platform today, although people have suggested this might grow to 20 to 30 million units by the end of this decade, which would give you then a 12 to $15 billion marketplace. But within all of this, our view was that LCDs are probably still going to remain quite the most important technology for supply reasons, for emphasis reasons of the different players, but LCDs will remain important. But AMOLEDs on glass and silicon are still there. And within the optics part of all of this, pancake lenses become the most important part. Again, this is a small subsection, about 20 slides out of the total 130 or something in the main market report. If you're an Epic member, please go ahead and find that if you would like to find this coverage, but also the coverage on AR. Jeremy?
Yes,
How
thank
did
you.
I do for time?
Just on time. Thank you very much, Jan. So we can take time for questions. So you can raise your hand through Zoom if you have any question for Jan. Yes, Gauthier?
Yeah, yes, can you hear me?
Yeah.
Yeah, I really enjoyed this talk. It was really nice. Thanks a lot, Jan. I have a question because I saw your background and maybe you could answer for me that question because I got interested into that market since a long time, I would say now. And my main question is, what do you think is blocking the adoption of AR or VR, especially to the consumer market? Because as you mentioned, like a lot of people are, showing the hockey stick since 20 years, and it's not happening. So, do you have a small explanation or like an opinion on that?
Okay, so let's do AR and VR and perhaps the segments of AR separately. I would say VR pretty much is a consumer device. I mean, it's used for gaming. I think if I was being bearish, this has been accepted within a range. I think the involvement of the gaming studios, which have been actually bailing out to some degree, right? Um, the availability of content, the availability of breakthrough games or experiences probably drives the VR marketplace together with overall headset price. Although, I mean, I've got an old VR headset sitting around at home. Why did I put it down? Because it was too heavy and it wasn't compelling enough, right? So I think there is still work that could be done to improve the consumer performance and the games that go with it. If you go to AR, then there's two completely different marketplaces, right? So the main B2B use in sort of warehouses, or if you're a Boeing engineer for B2B heavy data centric applications, that's less than 1 million units, but that could grow quite nicely. But it's a B2B sale of highly sophisticated technology. The power, display, content, heat circle is horribly complex, right? And I think Carl Guttag and others have really made it very clear that just you change any one of them to make them better, it has impacts on all of them. This is just a very, very, very difficult set of engineering problems, right? The one that's really taking off and is a consumer trend is this first-person viewing display glasses thing that actually at the moment doesn't have displays at all up until the launch of the Hypervision product, which was the one that has just come out, right? $8.99 or $7.99, but they're sold out and it seems to be going into the marketplace quite well. I'm sort of surprised that a fairly simple LCOS display in one eye only is actually being reasonably acceptable. So I'm looking forward to seeing that grow. Everybody I've spoken to has said, well, the next phase for that is binocular, but by the way, Ian, be careful because as soon as you move to binocular, the problems don't go up double, they go up triple or quadruple.
Yeah, yeah.
Um, I think the one that people are excited about is that space, right? And I think it'll be really interesting to see whether or not the actual product performance elements of this can be brought together, right? The for now it's an OmniVision LCOS that's then with a Lumos reflective waveguide. Whether that then becomes many players offering micro LED and hence product centric competition to improve the product and multiple big brands supporting this, that could be really interesting. But this one is actually beginning to move. So that's the one I'm actually most positive about for now.
Thanks.
Thank you, Gauthier, for your question. Any other question for Jan? And yes, if not, yeah, it's good to remind that you can have access as Epic member. You can have access to the full report, on the Epic website. So feel free to check it. And if you have any question, you can contact Jan or you can contact the Epic team as well. So thank you, Jan, again,
Thank you.
for participating and for opening the session. And see you next time.
I have to go now. Thanks very much.
Yeah, I know. Bye-bye. Thank you. And now welcome our next speaker, Uwe Vogel. You are a Division Director of Micro Display and Sensor at Fraunhofer IPMS. And you will talk, Uwe, about high resolution display for near to high virtual screens, requirement and achievement. So please, Uwe, the floor is yours. Thank you. And you are muted, Uwe.
Thanks for the hint. Can you see my screen?
Yeah, all good.
Okay, thank you very much. So, well, I was already introduced, so I will focus on micro displays. Obviously, that's all also are being used, as we have already heard from Ian, for near to eye virtual, let's say, virtual reality displays and screens and headsets. And well, I mean, maybe a few words about Fraunhofer IPMS. IPMS, by the way, stands for Institute for Photonic Microsystems. We are based in Dresden, Germany, and one of the, let's say, major advantages of this region here is that we are, let's say, heavily surrounded, but also, let's say, working and collaborating with our friends from the semiconductor industry. So we have fabs here almost in walking distance. I mean, here you can imagine this is Dresden Airport, and then it's really, let's say, walking distance to fabs of Global Foundries, Bosch, or nowadays TSMC, or actually a joint venture. ESMC is constructing a new wafer fab here, and also directly here on our campus, we are located here with our X fab in Renesas, and also almost in walking distance also in Finland is even currently extending their fab over there. So it's really a major hub of microelectronics and semiconductors in Europe, and every chip produced in Europe actually comes from this area. To make micro displays or to develop micro displays, you actually need two major core competences. And one is the IC design, which is necessary to well, to assemble more or less, let's say, on an electronic design automation tool, all the hundreds of millions transistors that finally are, let's say, needed to individually address and drive tens of millions pixels on such a tiny screen. And on the end of the day, something has to light up, and that is, in our case, an emissive front plane integration. So OLED is obviously an emissive front plane technology. It's widely known from smartphone displays nowadays for many years already. Nowadays, let's say the more than 50% of all new smartphones on the market are coming with an OLED display or with an active matrix OLED display. So really, let's say, to make such sort of displays, you really require these two major core competences. And in our case, we actually work with semiconductor foundries, so with wafer suppliers to actually produce some silicon wafers, backplane wafers based on our IC backplane design. Then we receive the wafers back from them and perform the emissive front plane integration into our own clean room. And that is, let's say, everything organized really, let's say, in one hand. So also, let's say, the IC designers and the front plane technology or process technology integrators are really, let's say, working with each other on a daily basis, and I think that is also one of our USPs. To elaborate a little bit on various or on different microdisplay front plane technology approaches, I mean, generally you have those where light source and image modulator are the same, and that is obviously true for emissive microdisplays like OLED on silicon, or maybe not yet mature but somehow upcoming micro LED on silicon, and also to some extent transmissive transmissive micro displays like OLED or LED on a transparent substrate are also to some extent emissive ones, but there are also all the other options where you need an external light source. So let's say light source and image modulator are separate devices, and obviously that also increases a little bit the effort for the optics that are required if you look at those kind of optics versus this one. And to those, let's say, non-emissive devices, also scanning devices like MEMS scanners, and also reflective ones like MEMS spatial light modulators like the Texas Instruments DLP or Elcos or such front plane modalities belong to. Let's talk a little bit about smart eyewear in general. Oh, sorry, here's a green frame somehow moved. In general, I mean, probably all of you are aware of the major differences between AR and VR, and I don't have to go into too many details here. But if you compare a little bit the major specs of fully immersive versus optical see-through, which is of course related to AR, or look around, which is some sort of that kind of optics. Also, Google Glass was actually a look around, let's say, optical system. And last but not least, head-up displays, so like in avionics or automotive. And if you compare the major specs like resolution, luminance, power consumption, frame rate, or latency, then you find out that for fully immersive, so that is, let's say, the VR headset approach, specifically very high resolution is important. So definitely more than full HD. Luminance is, if you compare it, let's say, to most of the other approaches, luminance is not so important here. And that's also one of the reasons why OLED, being a mature technology and easily being able to provide luminances up to 2000 candela per square meter full color, is probably best suited, at least if you talk about micro displays, is probably or OLED on silicon is probably best suited for VR applications as well. Power consumption depends. I mean, if you have a Tesla device, then power consumption is probably not that much of an issue. But if you're talking about a untethered device or compare it to such kind of, let's say, approach, yes, this is a look around optic, but where you obviously have very limited battery capacity, then power consumption becomes important as well. Frame rate, I mean, think of effects as motion sickness or so, and also, let's say, somehow related to latency. I mean, these are really, let's say, critical requirements in VR. So very high frame rates, very low latency. That is really a must have in VR headsets, and therefore also on the specs of such a display. And at least in the past, there was some trend that smartphone displays, which I mean, smartphone displays are of course, or let's say in the past, smartphone displays have been regularly used as let's say as display screens for VR headsets as well. And as also, as Ian already mentioned, let's say the VR market portion is of course much smaller than that of smartphone displays in general. But I mean, the smartphone display industry and the smartphone market has also been kind of a driver for specifically with respect to pixel density for VR panels. So how has it developed in the past? And here I have made a let's say some sort of research on how the pixel density in PPI of high-end smartphone AMOLED panels has evolved by their release date. So I started that somehow in 2010, and then it was rather, let's say, interesting that in between, let's say, 2014 and up to about 2020, let's say the majority of the at least high-end smartphone AMOLED screens was in the range of 500 to 600 ppi, some even beyond that. But that has come down again a little bit. So even if you look at these high-end smartphone or flagship screens, then nowadays you have just 400 to about 500 ppi anymore. There's a reason behind it, and that reason is obviously cost and yield, which is, or let's say, well, which are both strongly related with each other. The screens became bigger, but let's say the pixel density did not increase too much, and that's a little bit in contrast to LCD. I mean, I did not really follow, let's say, the LCD smartphone development or smartphone screen development too much anymore, because the majority of smartphone screens nowadays is OLED. But here already you could imagine that LCD to some extent was able to provide higher pixel densities than OLED. And even nowadays, the highest PPI smartphone display with OLED is 520 ppi. What do we need in VR specifically for large field of view? So where we actually also talk about pixel per degree. And that is one of the earlier examples. So Samsung Gear VR equipped with a Galaxy S7 display at 577 ppi, which is even higher than is, let's say, typical now. And therefore, at a 101 degree field of view, they have been able to achieve a 13 pixel per degree angular resolution. Now let's look at the human eye resolution. So that has been, I have to say, considered at a limit of about 1 arc minute. And if you translate that into let's say a 160, 175 degree field of view, at a 60 pixel per degree, which would translate into the 1 arc minute limit, we would need actually 100 million pixels. And if you put 100 million pixels on an, well, about 5-inch screen that is used for VR headsets, for instance, then we would need to come up at about 3000 ppi. And if you compare that to the current, let's say, available PPIs, at least in smartphones, we are still away from that. There has been recent research on the human eye, let's say, resolution, and that was just even a few days ago, I think, in Nature Communications, and they came up that at least under certain conditions, so for instance, for foveal achromatic vision, the eye might achieve even 94 pixels per degree, and for certain, let's say, color approaches and setups, 89 ppd or 53 ppd. But I mean, for the moment, let's still assume the 60 ppd about. What do we have today? MetaQuest 3 is equipped with a single LCD TFT, 1280 ppi, 25 ppd. Sony PlayStation VR 2 AIM OLED TFT by 2, 800 ppi, and come up with an 18 pixel per degree angular resolution. Apple Vision Pro has already been mentioned with an OLED on silicon, OLED micro display, or 2 of them, and each of them 33386 ppi, and that translates into a 7.5 micron pixel pitch. And with their optics and that resolution, they already achieve 34 ppd. But there's also the fill factor issue. If you look at a mobile phone or at a smartphone display with a microscope, then usually you come up with such sort of view. So that means that the actual fill factor in such a smartphone display is about 25%. So actually, most of the area is black. And whereas on an OLED on silicon display, you can achieve, that's an example from us, so 10K DPI OLED micro display. And 10K DPI means 2.5 micron dot pitch. So here you can imagine 10 micron for subpixels or for dots. And here we have above about 200 nanometer gap, and then you come up at about 85% fill factor. And that is really important to actually reduce the screen door effect in VR. So if you have such a small fill factor, then you come up with a screen door effect. If you have a large fill factor, that's much, much better. So actually, there's kind of a conclusion already, let's say, from these few parameters. So micro displays really provide a higher resolution than TFT backplanes, and they are kind of, let's say, even a nice platform to even develop, let's say, high resolution or high PPI display approaches that might achieved in TFTs later on. But at least for now, and with respect to resolution, micro displays is directly, let's say, is the best choice. But there's more than that. I also mentioned lowest power or low power consumption. Typically, displays or most displays on the market, including micro displays, are frame controlled. So that means you need a continuous scanning of all pixels. But that approach also enables high frame rates, which is important against flicker or motion artifacts. We already addressed the motion sickness issue. Of course, that always comes with high bandwidth. Externally, let's say in your system, you need a video controller to continuously supply the frames at very high frame rates with the many pixels. And high bandwidth typically comes with substantial power consumption. So, but obviously the use cases for that is in most of VR, which you see through AR, MR. But there's also a memory-based approach where you just transfer those pixels that change from one content to another, and that even enables you to come up with frame rates that go down to 0 hertz. And I mean, that's maybe not the best choice always for VR applications, because let's say due to this motion sickness issue, you need to be able to provide very low let's say, very high frame rates, even at minor movements of your head, you have to follow very soon. But that actually means that you need a very low latency, and also low latency can be achieved by this approach because you come up with a very low bandwidth requirement, and that actually enables ultra low power consumption. Still, let's say the major use cases for that are best for this technology are assisted reality or optical see-through AR. But then let's move to high pixel density again. The backplane processes depend, or let's say the resolutions that you can achieve with pixels heavily depend on the backplane CMOS process nodes. And there are so-called deep submicron CMOS process nodes, for instance, at 28 nanometer. And there has been a project that we have performed together with GlobalFoundries here in Dresden on their 28 nanometer CMOS backplane process. And by that, we achieved at a 0.18-inch screen diagonal 10,000 DPI monochrome resolution. And we have not yet shown that, but that also translates into 5,000 PPI at 4 subpixels full color resolution. So 2.5 micron dot pitch. And again, let's say by combining this frame controlled and memory based architecture, we are now able to achieve a very high frame rates in general. So here, for instance, up to 480 Hertz. That also let's say that also depends on the use of this deep submicron CMOS backplane process. But we can even go down to 0 Hertz by that. And we can even achieve, that is specifically important for LCOS, for instance, where you typically write backplanes into the front plane. There we can achieve an internal frame rate even going up to 10 kilohertz. So you can really have a low to high bandwidth interface according to, let's say, customer requirements. And so you actually, as a user, can really trade performance versus power consumption. So with this flexible architecture, you can actually achieve both high pixel density video and low power requirements. There are more, let's say, there are more features that will also assist virtual reality. For instance, eye tracking based on our bidirectional OLED micro display, where you can have both, for instance, 4 subpixels for emission and the 5th subpixel for detection. You can perform embedded eye tracking, or again, large area OLED micro displays that are definitely capable in providing higher resolutions in full HD. For instance, this 1-inch screen diagonal WUXGA OLED micro display has made it into a device of a Spanish company, Limbax. That has been acquired by Apple, I think early last year, and they made use of 4 of our of those micro displays, so 2 per eye, to achieve an about 26 pixel per degree resolution. Okay, so to also provide an outlook, so high brightness is obviously a topic for us, not that much for VR actually, but specifically for optical see-through AR and also some non-imaging and non-display applications. High resolution, the talk was a lot about high resolution, and high resolution is also important for, let's say, even higher pixel count. So for instance, light field and holographic displays will require, let's say, not just 10 million dots, but maybe 100 million dots and more. On the other end, if you can make a small chip with still with a very high pixel density, so millions of pixels, let's say, on a 0.2-inch screen diagonal, then you can make such a display, at least display component, at a lower cost. So high pixel density is always important. Then also embedded sensing, embedded computing, connectivity, and also new form factor, like for instance curved devices, that can really help in optimizing or improving the optics. Yeah, that's it. Maybe also to conclude a little bit, we are looking for system integrators and application partners, and on the other hand, offer custom-specific R&D and pilot fabrication of such kind of devices. Thank you for paying attention to my presentation.
Thank you, Wei, for your nice presentation and overview. Any question for Wei? We can take one question. Okay, and if not, I would like to thank you again, Wei, for your nice presentation. And we will move on with our next speaker. Thank you again, and we welcome Gareth Jones. Gareth, you are Director of Business Development at IQE, and you will talk about micro LED P wafer.
Can you see my screen okay?
Yes, and we can hear you. Oh, good.
Okay, so yeah, thank you for inviting me along. I'm probably furthest up the supply chain in terms of supplying the sort of base materials that go into micro LEDs that are an emerging part of the displays field. Thank you for Inouye for introducing micro LEDs in some shape. They are an emerging technology, particularly for AR applications where you need high brightness to compete with ambient lighting, but also sort of extremely small form factors, and lend themselves extremely well to integration with backplanes. So I'll just briefly introduce IQE to you, so we sit upstream at the end of the supply chain, forming epitaxial growth. So I suppose that right at one end of the supply chain is the raw materials, and then those raw materials are grown into what are called substrates, and then those substrates we put into our epi wafer reactors, and we grow various layers that I'll talk about a little bit in the next few slides, using reactions based in two types of growth chambers. One is what's called an MOCVD reactor, which is metal organic chemical vapor deposition, or an alternative, more precise, but maybe sort of lower production capability reactor is known as molecular beam epitaxy. They're both similar. They both essentially deposit semiconductor materials monolayer by monolayer in very precise detail that allow us to formulate the device type that is then used in the chip fabrication processes. So IQE sits in the middle, and we feed then epi wafers to the foundries or to the integrated device manufacturers that then will process and dice the chips that will then go into the packages and systems that are used for displays technology and many other types of processes as well. So we not only manufacture epi wafers for LED applications, but we also produce laser diodes, vertical cavity lasers, photodiodes, and electronic transistors such as high electromobility transistors and heterojunction bipolar transistors. We've got a long history. We've been going for coming up to 40 years. A long history in gallium nitride, which is one of the main materials used for blue and green LED technology. And we were an early pioneer in the red space also with aluminium, gallium, indium phosphide materials. So just moving on. So just to talk a little bit about micro LEDs. There is a misconception in the industry about micro LEDs. Are they just small LEDs? Well, they're a little bit more than that, and they get confused quite a lot with what are called mini LEDs. And in displays technology, there are two ways in which you can use these LEDs. You can use them as a backlight to effectively provide the light that is then modulated and transformed in something like an LCD or an LCOS device. And that is where a mini LED may come in order to provide a modulation to the background light that might give rise to better contrast, for instance. Micro LEDs are a little bit different. So in a micro LED is designed to be an active pixel. So it's part of the image forming characteristics that will be used in the active display itself, rather than just being a backlight, an addition to an image forming device such as an LCD or an LCOS. They do, as you'd expect, also differ in terms of the size of the system. And just help me out here. Can you see my mouse, or do I need to use the laser on this?
No, we can see your mouse.
Oh, excellent. Good. So this is a graphic that shows a standard LED that you might find, for example, in a street light or a light bulb, typically up to about 1 millimeter in size. As you can see, also standing quite high above the base. Standard LEDs were the first type of LED that usually came out, typically about 200 to 300 microns in size. Then you see what are the mini LEDs, and these are the ones that act as the contrast enhancing backplane for LCD technology. And then the tiny, tiny dot that you see right down the bottom of the yellow square there is a micro LED. So not only is it very small in size, it's also very, very thin. And that lends itself very well to producing very small form factor display systems with extremely high resolution. And because these are very efficient light emitters, they also have a very high luminance capability. And you can see that blown up on the middle image, where we've got a mini LED. So this is of the order of maybe 100 microns or a couple of 100 microns. And then micro LEDs are actually going down to around about 1 micron in size, and only a couple of microns in height. So if you imagine, but still extremely high brightness. So these things are enable you to go to very, very small displays with very high resolution and very high brightness. And you can see that in a little bit more detail here. For instance, this is what is probably the industry standard for microLEDs using displays at the moment, which is 15 microns by 30 microns. And these are built, typically they don't live on their own. So they're built as high density arrays. They don't have really much of a role on their own, whereas a standard LED could sit there as powering a light bulb, for instance. Micro LEDs like to live in families and densely packed arrays in which they can be switched on and off very, very quickly to produce the information that's required for display technology. They are very energy efficient, especially the blue gallium nitride based LEDs are very robust materials. They can be embedded in quite hot environments and will still perform for many tens or even hundreds of thousands of hours. And the reason we're confident of that is because these have been tested for the last 20 years as the main light source in traditional lighting applications. And we now have reliability data stemming for hundreds of thousands of hours, some of which, if they're treated properly, will really not degrade very much at all over that lifetime. So from IQE's perspective, we engineer the layers that are built up from what I described as the epitaxy process in order to provide the functional display, the functional device that will be the micro LED display. So as I mentioned before, we start off with the substrate, which could be, for example, silicon or sapphire, or gallium arsenide or germanium, depending on the material system that we're using. And then we add another series of very precise layers that are either N-type, undoped, or P-type. And those layers are put together in a very precise order, and that allows the active device structure to be formed. So this, for instance, is known as a PIN diode. And by applying current from the top through the device, you end up with what's called radiative recombination in this region in the center, which is a multi-quantum active region, and it's extremely efficient at producing light. And you need these other layers really to support the injection of the current that's going to be going in and then is captured in this region in order to produce the light. When we talk about the scale of this. This is a electron micrograph of some of the layers that will be in this region here. So these are called quantum wells. They're extremely small. So this is about 100 angstroms in size. Each of these small white bands, 100 angstroms is 10 nanometers, or 10 to the minus 9 meters. You can see here, when we get down to really, really small scale, these are actually atoms, individual atoms built up in the crystal together, for example, in something called gallium arsenide. These will be called monolayers, so groups of atoms in a crystalline lattice. So we're essentially producing micro LEDs by doing nanoscale engineering. And what is interesting for this, which is not shown on the graph, is a useful understanding of the precision required that we work with, is that a 10 nanometer thickness is what we control to over maybe a 200 millimeter diameter wafer. And it would be the equivalent of growing layers with the thickness of a human hair over the size of a football pitch. So that's the sort of scale of thickness to diameter or width scale that we have to engineer at in order to produce these devices. And the same level of engineering would go into a transistor or a photodiode or a laser device. So how do we do that? Essentially, we particularly for micro LEDs, we would use something called an MOCVD reactor. And here in this reactor, we flow gases over these substrates that are rotating. The gases would be things like trimethyl gallium, ammonia, phosphine or arsine, that are then cracked in this reactor chamber. So there would be a lid over the top of this, and the gases flow in a very thin layer over this. And as this is spinning, you get an average of the gas flow within that. They then form a reaction that then sticks to these wafers, going from the gas phase to the solid phase. So we would put trimethyl gallium over the wafers and arsine, and those would be cracked and they would produce gallium and arsenic that would then stick together on the surface after sort of traveling around on the surface for a little bit. And that would make gallium arsenide. And gallium arsenide is a fundamental part of what would make a red LED, for instance. If you took trimethyl gallium and you added ammonia instead, which contains nitrogen, then you would create gallium nitride, which would be something that emits blue light or green light. And if you're really good at growing these things, it can also produce red light. To give an idea of the scale of this, this is a 200 millimeter wafer, so 8 inches in diameter, and we can grow 5 of those within that run. And one of our partners, Aixtron, is a world leader in producing these types of reactors. And so by doing this, we take our substrate, we produce these layers very precisely, and that is what we then sell to our customer, either as a micro LED or as a laser or as a photodiode, etc. So what do we care about? Well, there are a number of things that we have to do really well in order that then our customers that are going to fabricate these devices will also have a good product. And yield is extremely important in the micro LED sector because the costs are already quite high, and we need to try and improve the costs to be competitive with devices such as the OLED, as Ian in a way described earlier. So we worry a lot about the cleanliness of the surfaces and making sure that we don't put materials in there that are not going to be compatible with our customers' process. So a lot of the new work that's going on in this area is actually doing wafer-to-wafer bonding between what we provide and then also things like CMOS backplanes, so that there can be an intimate coupling between the micro LED device and the electronics backplane. And by doing that, the aim will be to scale up and minimize costs in this area. We worry about thickness uniformity and compositional doping uniformity, because we want every device that's produced on this wafer to be the same and behave the same. And this is quite a feat to do when you think about it. So making sure that human hair is the same thickness over a football field. So it's quite a challenge. When you put these materials together, so when, for example, we grow gallium nitride on top of a silicon substrate, the materials, gallium nitride materials and silicon materials, have different mechanical properties, and they don't want to go together that easily. So we have to manage the interfaces between the materials, and then manage the strain that gets built up in the materials. Excuse me. And what it does when we're growing these epi wafers, if you get that wrong, basically what happens is the wafer curls up in the reactor and can't be used. So we have to manage what's called the bowing shape and size of the bowing of these wafers to make sure that they can still be used and through the fabrication steps of our customers. One of the key killers for microLEDs is defects leading to pixels out. And because the microLEDs are tiny and they're densely packed, it creates a big challenge to make sure that we can produce these arrays with no defectivity effects, so no pixels out due to defects. We also then, because these arrays are quite large, the micro-LEDs themselves are very small, but the arrays are quite large. Defects, even one defect on quite a large array can mean that array becomes unusable. So we've got challenges at the very, very small level and the very large distribution of those defects. And of course, the interface layer quality determines whether it's going to be an efficient device or not. So that's our business, is to worry about these aspects and to try and make sure that our technology is as useful as possible for our customers. Here's an example of the reactors. As a row of identical reactors. Actually, these reactors do not need a lot of human intervention. So they're all robot loaded and cassette to cassette loaded. And that's the way we can scale up and get the cost down in our part of and contribution in the industry. So when we provide these wafers, we grow the epi wafer on our substrates. We can grow them by changing the material system and the layer compositions. We can make a red epi wafer, a micro-LED epi wafer, or a green or a blue. Our customers would then take those, and for traditional display applications, they would then pick and place these onto the backplane to produce the color combinations that they need. And then the backplane would act as the driver device for each of those pixels producing the display. And here's an example of a finished device, for instance. The way in which you might do this in the future for particularly for AR applications, which are probably one of the smallest form factors that you need for these devices, maybe by combining the colors together on a single epi wafer, so-called monolithic integration, and then wafer bonding that epi wafer, which has got the three colors on there, onto the backplane, which might be a CMOS backplane, or stacking them as well. You can also stack these up such that they would emit the three colors in the vertical direction, but they would be formed of different wafers, which are each emitting the different colors. And again, you would then put that on the backplane to allow the integration with the driver electronics. In terms of the competitive situation, micro-LED, as has been mentioned, is a extremely efficient, very bright source, but it's also, there are downsides. It's also very still one of the earliest technologies to be used in the displays as a pixel, and it's still quite expensive. So I hope I haven't been too bullish in putting green down the list here of comparisons versus LCD and OLED, but at the moment, the progression of micro-LEDs into the industry is hampered very much by the high cost. And that high cost comes from the cost of the materials, like the epi wafers, for instance. And around 50% of the cost of a micro-LED display is the micro-LED array itself. And a lot of that is driven by the downstream aspects associated with the mass transfer process, where you are effectively taking the LED pixels and placing them on the backplane. That's fraught with a lot of challenges to be able to do that at extremely high speed and very low defectivity. But also then when you do have a defect on there, you have to repair that, and that repair process is extremely costly. So that's driving a lot of the costs, and it's where a lot of effort is going in the industry at the moment to improve that. If we can tackle that, then all the other attributes are extremely positive towards micro-LEDs entering as many of the display end user cases as possible. And this chart here, for instance, shows...
Gareth, sorry, you have to finish now, please.
Okay.
Yeah.
Okay.
Yeah, a few minutes more.
Okay. This shows essentially where currently the opportunity for differentiation versus organic LED comes in, and we know that the AR space is particularly one where micro LEDs is looked to be produced, and TVs is probably one of the most difficult at the moment. Although there are Chinese manufacturers that are looking to produce producing micro LED TVs, but they're extremely expensive, hundreds of thousands of euros per display. I will go to just one case study, which is the RGB micro LED projectors. I think Ian mentioned Jaybird, and this is the Hummingbird micro LED RGB array. So these are micro LEDs that are then combined in something like an X Cube or another combiner to produce the with an LCOS display driver. So they're just the light sources for the LCOS to produce AR display technology. So thank you very much for your attention, and sorry I've gone on a little bit too long, and I don't know whether we've got time for questions, but thank you very much anyway.
Thank you, Gareth. Thank you very much for your nice presentation. One question for Gareth. You can raise your hand through Zoom. And if not, let's thanks Gareth again. Thank you again, Gareth, for your nice presentation.
Yes.
And now we can welcome our next speaker, Stan Larocque. Stan, you are a founder at Lynx Mixed Reality, and you will talk about display and optics for MR. So welcome.
Hi. Yeah. Thank you very much.
Thank you. We can see your screen. You can start. The floor is yours.
Okay, that's great. All right, so I'm Stan Larocque. I'm the founder of Lynx. I created this company 6 years ago. We are based in Paris, and we design and build mixed reality headsets, more like pass-through headsets. So we're moving back on the other end of the supply chain now. We are more on the product side of thing. I'm an integrator, meaning that my team either take existing stuff off the shelf, or sometimes we build things ourselves, and we actually build a product that end up in the consumers and users across the world who use mixed reality to solve their problems. The company is focused more on B2B applications, so this drives also our decision regarding the price of the product and so the components we can use, because our customers are not they're not necessarily gamers. The like price is less of an issue. We don't need to build $200, $300 headsets, which is near impossible if your name is not Mark Zuckerberg. And I will hint at some of the things that were said in the first presentation today, which was very interesting about the market evolution. And as I represent a company that has access to the roadmap of Chinese and Japanese display suppliers, I can probably see for the next 2 years like where the direction is headed in terms of focus for this market. So as I told you the headsets we're designed at Lynx are used for B2B applications. And basically, when you look at the market for headsets today, it's either marketed as a gaming console, which is the one that maybe your children or your nephews got for Christmas, and then they left on the shelf for a few months. And our users are using the headsets for anything but gaming. And when you think about it, they're using it for professional training and remote assistance. And professional training is just serious video games. So we are using like the same pipelines, the same software. We don't need to rebuild everything. We just design a headset in a way where it makes a bit more sense for our users to pay a bit more money to get rid of some of the problems you're seeing with consumer headsets. And one of the issues, of course, are displays and resolution and optics and ergonomics. Some of our users even take those headsets quite far, maybe a bit too far. It's used in some surgery and also surgery training, which meaning that even though the market for VR, I still call these products VR because they are VR, and VR basically became MR in some ways in most companies now. These products they solve the real problem. You can say whatever you want about the convolution of the market and how it's artificial. I will completely agree with you when you're talking about the consumer market. The consumer market, for me, as the first defender of those products out there, is completely artificial. The devices, the supply chain, and most of the components out there is heavily subsidized by Meta, who, let's all remember in this call, is losing $1.5 billion a month on the VR and AR activities. It's not like expenditures, it's the loss. So, expenditures is actually much higher than that. So the market is heavily subsidized. And this is why, as a European company with different business model, different ethics, and also different customers and vision for these products, we targeted a different set of use cases where we think the real value is. I really wanted to show you this picture. On the right is the first device I built myself when I started Lynx, the company, in 2018. I was alone, and I built a headset that was used by surgeons to train themselves. And on the left is a real picture 100 years ago, almost exactly 100 years ago, of this class of people, surgeons, trying basically to do the same thing. They want our users, they want to see what they cannot see with their own eyes. They want the headsets to give them superpowers, to bring back in the visual field what is not seen easily by the eye, either in spectrum, either in contrast. And on the left, I think the two people on the picture, they died shortly after with all the radiation from the X-rays tubes. But this is, probably a different story to tell. But the people we are addressing today, either in defense, medical, or industry, they have been dreaming of the technologies we're building for 100 years. So it's really satisfying today to see that, as an industry, whether you're selling displays or stuff built on wafers, we can address needs that were forever in the minds of those people. So it's really a great satisfaction, I would say. It's still also very hard, and there is a lot of things to do. We built this first product. Maybe some of you have seen it over the years. This was the Lynx R1. We're done with it. We shipped whatever units we could ship, a few thousands of them. We built everything. So everything you see on the picture was designed by engineers in Europe. And we worked with Taiwanese manufacturers. And the optics it was really curious at the time. I think one of the aspects of my company is that as a startup, we don't want to copy exactly what is out there in the market. We don't want to copy Meta headsets because the consumer, even if it's a professional, he will compare the products and say, well, they're both great, but the Meta one is cheaper because it's subsidized. And then they become a Meta customer, and we don't want that, right? So we differentiate ourselves with the choice of optics and displays we're using. And I'm here to finally talk about it. It was in the news over the weekend, but our next product is going to be revealed in January 21st during a SPIE AR/VR conference in San Francisco. And I will talk more about the optics and the display we're using. I've been kind of teasing it before. So this is what we used before. You can see a side view of the display here. If you can see my mouse, I don't know if you can see my mouse, but we use the LCD panel.
Yes, we can.
Yeah, okay, great. We use the LCD panel for all the good reasons the first presenter explained. Cost, availability, resolution that is already quite good. Also the pattern on the display compared to OLED. But mainly the cost was the big driver, because back in the day, like 2019, 2020, OLED panels were not even micro OLEDs, but like OLED panels were still very, very much too expensive. And so we used the Japan display. We could double source with Japan display and BOE, 2.1-inch LCD panel. And the optics is actually from Limbach. I don't know if you remember that company, but in the Fraunhofer presentation, you could see a Limbach product in some of the slides. Limbach was a Spanish optical house company designing this 4-fold cathode optic prism, which at the time, between the Fresnel lens and the pancake lens was great, because you could have the compactness of the pancake lenses, and you don't lose the brightness, you don't lose the contrast of the image. So this was a killer. This was a killing design. This was amazing. One of the main problems is that there are 12 freeform surfaces on this piece of optics. So you can imagine the tomography on that beast. But we managed to diamond turn and also manufacture that at scale. It's really hard to manufacture. We had some defects that we had to manage with calibration afterwards. But that was a very nice piece of optics. I'm actually very happy that we shipped that and that we proved that we could do weird things. But today, they are even slimmer optics. I want to show you this research made by Meta. They published it in August during SIGGRAPH 2025. They showcased a curved pancake lens that brings very high field of view to a supposedly compact headset. You can see on the picture that it might be compact, but it's still kind of bulky because it's a research prototype, but we can imagine that maybe a production device could be much slimmer. The funny thing is that they released, like Meta usually released, research stuff like that during SIGGRAPH almost every year now. And none of that stuff is shipping in actual products. I've never seen something that this research group, so Doug Landman and his friends at Meta, they're doing amazing work, but we have not seen a lot of things shipping in actual devices. What I'm happy to tell you is that our next optics in our next headset is actually the thing that Meta showed a few months ago, saying, "Oh, this is for the very far future. This is R&D. We don't know when it can be available for mass production." And actually, we pulled that off. We are designing exactly that, a curved pancake design. So I can show you here as an exclusive, like some side views of the optics. You can see we are still using an LCD panel, so much higher PPI, much higher resolution. It's a LTPO plus COA panel. I will not leak the resolution today. I'm keeping that for the on-stage presentation in January, but it's a really high PPI panel, a nice upgrade compared to our version 1. And you can see the two pieces of optics here. What you can notice is that there is no flat surface in the design. There are 4 surfaces for 2 lenses. And the difficulty in that design is not building those 2 kind of aspheric lenses. This is the easy part. The very difficult part is in the middle here, which is not symbolized here in the CAD file. In the middle, in the air gap between the 2 lenses, you need to have a quarter wave plate and a reflective polarizer to actually polarize the light. This is how a pancake lens is working. And because you don't have a flat surface, how can you laminate something on something spherical, right? So the Apple Vision Pro, what they did is that they built a cylindrical pancake lens, which is smart because on a cylinder you can laminate a film quite easily. On a sphere, you need to think outside. You need to think outside of the box, and this is what we did. I will probably share at some point how we did it, but it's the first design where everything is curved. What is interesting is that because everything is curved and like optimized for display, you cannot beat this design. You cannot. There is like, if you're staying in the realm of pancake lenses, you cannot beat a sphere. It's like you cannot bring more field of view in the design through a different optimization if you need to compromise on flatness. And we designed with this optics with Hypervision, which is an Israeli company. We invested our own money in this company because if you remember my story about Limbach, we didn't invest in this company. And so they got acquired by Apple in January 2023. So that was a disaster. They're enjoying their retirement at Apple now, I'm sure. I know. But it's too bad that Europe lost a great optical house there. So with Hypervision and Lynx, now we're playing a bit more aggressive. And we have this design, and I'm very proud of it because it's mass produced and it's going to be showcased in a little less than 2 months now in San Francisco. And you can see that there is only 16 millimeters TTL, between the first element of the lens and the display. So it's a very thin eyepiece, and on the left you have a right eye of what you will see in the headset in the future. So this pancake lens, like some of the presentation showed us earlier today, is expensive. It's more expensive than the optics we built with Limbach, and it's more expensive than the Fresnel lens, of course. But the compromise is so great for us. We are going to have the largest field of view of any standalone headset that has been on the market. It's a lot. It's more than 120 degrees. It's something that people have not. A lot of people don't have experienced such large field of view before. And also at the same time, we are able to reduce the total track line, meaning that the pass-through cameras that are behind the display and in front of your eyes, they are smaller. They're closer to your eyes, meaning that the parallax effect of the pass-through camera is diminished. This is why we invest so much in optical solutions that are reducing the total track line between the eye and the camera, not the display. You need to think about the system is how far is my pass-through camera away from my eye, and you need to ideally, and we've seen that you can find some papers on the internet. There are some optical designs where optically speaking, the camera is at the same location as the eye. It's quite magical. It's quite expensive and not practical for any headset today, but this is the end goal. This is where we want to go. So this is why we're ready to pay 5 times more to have this piece of optics in our headset. Also better MTF than any Fresnel lenses. I mean, there are a lot of things you can say comparing Fresnel lenses and pancake lenses. You can also use the headset without the foam in VR if you want the peripheral vision, you know, available to the user, which is also what we did. I'm a headset builder. I design and I build them with my team, and we've seen this industry now for 7 years. We've been deep down in this industry for 7 years. So I just want to bring my 2 cents to the smart glass bubble that we're seeing. I will call that a bubble. It's not the AI bubble by any means, of course, because nothing else is close to that. But there is a bit of too much of an enthusiasm for smart glasses, because the issues we're seeing with smart glasses that were not solved during the Magic Leap and HoloLens era are not much more solved today. Sure, you have very good monocular micro LED. I will give you that. And they're great. You've seen the event glasses released last week. But I think we are losing sight, not to do some bad games with the words here. We are losing sight of what what a piece of glass is. It's a medical device. I'm not wearing glasses. I don't want to wear glasses. And if I would need to wear glasses, they would have to bring a lot of value to me. I think you're all wearing glasses today, some of you in the assistants, because they're bringing a lot of value to you. They are solving an eye problem, a medical condition. And so you need to clean them, you need to pay for them, you need to not lose them. And now in the future, I will tell you, oh, you need to charge them, you need to update them, you need to deal with them like any other piece of electronics, which is, a lot of care. And, a previous presenter said it, Carl Kutag, famous for that, talked a lot about the forthcoming issues with smart glasses. So I think as an industry, and what we can promise to the consumer and to people like me who are actually building the devices, we need to be extra careful of managing expectation. I want to add another comment. A lot of my friends saying, oh, but Stan, you don't understand. Glasses are not a medical device anymore. It's a fashion accessory. Sure, okay. But as it is written in my slide, I will say it in a more improper way, but I have yet to see a woman wear a pair of smart glasses. The Meta display, the Meta Ray-Bans, they are the fastest selling Ray-Ban in history. But I mean, geeks are buying that. I'm not sure they're really building fashion out there. So I don't know where this market is going. I'm looking where I'm in this conference. I'm in the microLED conference in Eindhoven. I was there as well. We're following very closely. I'm just extremely cautious about the content and expectation the consumer can have with those devices. On the other side of the spectrum, I'm aware of the issues of the class of devices I am building, which are bulky headsets that are still looking like a brick you put in front of your eyes. So, to close on that, there is no easy solution, no easy way. I'm just, I've seen a lot of bubbles. I've seen the VR bubble. I've seen the AR smart glass, from Magic Leap days. We need to be cautious, please. That's just my word for today. I'm excited to show you my next device in January. And of course, I want to close on the LCD panel stuff. I think LCD is going to continue to grow a lot, because the two biggest players, I don't think the slides were completely right about the market analysis. I think, I don't see a lot of mention of TCL as a display provider, but TCL is the biggest display provider in the world today. They build most of the TV screens. And I've seen, when we look at their roadmap and BOE as well, those two companies, I think, provide displays for Meta, for Valve, with the Steam headset. And when I look at the roadmap, I don't want to breach any NDA, but the market for LCD VR panels is going to change end of next year and over 2027, when you're going to see around 2-point-something LCD panels that are going to bring 3K and then 4K resolution. I think this is going to, and with the architecture and the electronics of the headset, when you look at the roadmap of people like Qualcomm, you're going to see that the headsets are going to be lighter and less bulky, with some compromises. And I think the market is going to change once again at when we'll reach this new generation. So it's not for 2026. It's for like end of 2026. You'll see the next Meta product at the end of 2026 and also early 2027. I think we'll see like the end of VR winter, like someone said. So that's it for me. Thank you very much.
Thank you.
I hope you enjoyed.
Yeah, thank you very much, Stan, for your nice presentation and sharing with us, this news and your point of view of the market. I will not be able to take some questions because we are running a bit late. But if you want to be in touch with Stan, feel free to contact me, or you can also discuss in the chat today. But yeah, it was very interesting presentation, and getting your point of view is very relevant for all of us, for sure. Yeah, thank you for sharing your email. So let's move on with our next speaker, Tobias Sorg. Tobias, you are Business Development Manager at Hensoldt, and you will discuss visual precision drives XR immersion. So please, Tobias, the floor is yours.
Yeah, thank you very much, Jeremy. Can you see my display?
Yeah.
Okay, so let's start. While today most of the presenters look at the hardware side of XR displays, I'm gonna focus on what matters in real use, so the factors that actually create immersion. Over the last few years, visual quality in VR has made an enormous leap. We've gone from images that clearly look digital to visuals that are surprisingly close to what the human eye expects in the real world. And that shift is really at the core of immersion, and you can actually see the difference. My name is Tobias. Hi, I'm working at the German company named Hensoldt Sensors in business development for research, technology, and innovation. And I'm mostly working with immersive technologies, simulation, and also computational graphics. And I'm also involved in several European research activities, and I'm part of the IDA CAPTECH groups on simulation technologies inside of those of you who know that. Quick agenda. So during the next minutes, it's not much time, but I will explore how visual precision drives immersion in virtual reality. So that's basically how convincing visuals make the brain treat a virtual scene as a real place. I'd like to start with how our visual system shapes the sense of presence, and afterwards look at some of the parameters that define the precision and with the challenges ahead on the way to truly seamless VR experiences. Just a few words about Hensoldt. Hensoldt is one of Germany's leading sensor houses. So we develop and manufacture sensor solutions across all major technologies. So that's radar, basically. It's LiDAR, it's electro-optics like thermal, and also sonar sensor solutions. The company operates across all defense domains, so that's basically air, land, sea, cyber, and also space. And we provide integrated sensor and data solutions for complex environments. With this expertise, we enable superior situational awareness and protection. Okay, so let's start with something simple. What you can see here are two images taken through the lenses of different VR headsets. So that's VR. On the left-hand side, this is what high-end VR looked like not too long ago. Visible pixels, it's limited detail, and the work that still feels like artificial, right? And on the right side, it's the latest generation. So near human eye resolution, natural contrast, clarity that makes the virtual world feel much more real. And what makes what's striking is not just the visual difference, it's the time between them, because it's just a few years. And this is how fast display technology is evolving from visible pixels to perceptual precision. And as these systems become sharper, faster, and much more coherent, something really interesting happens. They stop being simple screens and stop becoming environments. And that's for sure. So immersion in VR really depends on how well the visual system can make sense of what it sees. Higher resolution basically means much more detail, better text readability, cleaner edges, for instance. And that pushes the brain toward presence because the image stops looking digital and starts looking continuous. Low latency is just as important. So when the system reacts instantly to head and body motion, for instance, everything feels much more natural and comfortable. And if there's some delay, the brain notices this mismatch and the experience becomes physically unpleasant. And there's optical coherence. So things like alignment, distortion, color consistency. When all of that is fine, the virtual scene behaves visually like the real world, and that's when reality or realism really kicks in. So in short, resolution drives presence, latency drives comfort, and optical coherence drives realism. And the brain needs all three to fully accept the virtual environment. And this naturally brings up the next question. What does a VR system actually have to deliver to achieve this level of precision? And that's where spatial, temporal, and also optical parameters come into play. So first, let's have a look at what happens when visual precision fails, so the immersion breaks, basically. So when the system doesn't quite keep up with how our eyes and brain expect to see. The first thing is we notice visual instability. So that's basically flicker, blur, or inconsistent focus. So eyes start working harder, trying to stabilize what they see. And this quickly leads to fatigue and also eye strain. And there's latency mismatch. That's exactly that tiny delay between your motion and the visual response. It might only be a few milliseconds, but that's really enough to make the scene feel like disconnected, you could say. And that's where motion sickness and disorientation start creeping in, for instance. So we heard it a few times. And the other thing is optical distortion. This is another big one, because when lenses aren't perfectly aligned over the image, and the image starts warping slightly, it doesn't take too much to make this feel subtly wrong for human beings. And finally, perceptual conflict. So when what your eyes see don't quite matches what the brain expects. A good example for this is the version accommodation conflict, for instance. So your eyes converge to look at an object that seems close, but they still have to focus. Or accommodate, as we say, and at a fixed distance, because the display is physically near your face. And that mismatch confuses the visual system and can cause discomfort and even nausea after a while. So once these cues fall out of sync, the illusion will collapse, and the brain stops believing, and the sense of presence finally is gone. So let's quickly switch from what the brain needs to what the system has to deliver. I think this is the interesting part. We can think of visual precision in three technical layers. So it's spatial, temporal, and optical, I already mentioned. So spatial precision is the obvious one. how much detail the display can show. So resolution, pixel density, contrast, color depth. That's what makes text, for instance, more readable or better readable, and fine structure visible. It's basically the how many photons and how many details we can offer layer, you could say. Temporal precision is a bit more complex because it's not just about being fast. It's also about being on time and consistent. Yeah. And so things like motion to photon latency, but also frame pacing, jitter, and also prediction. The system has to update the image in sync with the user's movement, with stable timing. So motion feels smooth and the world just feels solid. If timing is inconsistent, even if the average latency is low, the image starts to wobble in time and the illusion suffers afterwards. And there, of course, is optical precision. Everything happens, what happens in the lenses and the optics. So alignment of the two eyes, distortion correction, chromatic aberration, how stable the image is across the field of view. This is what turns all those pixels into something that actually looks geometrically and color-wise correct. So where to go from here? I think we all noticed, even with all the progress we've made in resolution, latency, and also optics, there are still major challenges ahead if we want to make VR to feel completely natural. The first one is full field fidelity. When we reach human eye resolution, not just in the center, but across the entire field of view. Today, most systems just give us sharp detail only where we look at directly. So this is foveated rendering. When we succeed to expand the clarity across the whole periphery, this is a huge step towards true visual immersion. The second is dynamic focus, to solve the vergent accommodation conflict, for instance. So to say, to overcome that would make virtual screens much more natural and less fatiguing. And there's also perceptual calibration. So every person, that's very interesting, every person sees a little differently because of our optics and also our attention patterns. They simply vary. And future systems will have to adapt rendering and optics for each user in real time. And last but not least, it's system coherence. This means basically aligning all those factors, so spatial, temporal, and also optical precision, so that they work seamlessly together. And when this happens, we move from just displaying pixels to actually reproducing perception. And this is the real frontier of immersive technology nowadays. Okay, so to wrap things up, immersion in VR really depends on how precisely we can match what technology shows us with how our visual system expects the world to behave. So visual precision isn't just about sharper displays or faster frame rates, it's about creating perceptual harmony. And that's a real goal. So not to build better headsets, but to build better perception. Thank you.
Thank you, Tobias. Thank you very much for your presentation. We can take one question for Tobias if we have. And if not, if you need to be in contact with Tobias, feel free to contact me or to contact Tobias directly through the chat. So thank you again, Tobias, for your nice presentation. And now we can move on with our last but not least speaker of the day. Welcome Beat Ruistaller, founder and CEO at Fluxim. And Beat, you will talk about enabling tools for research in emerging displays. So please, Beat, the floor is yours. Thank you.
Thank you very much, Jeremy. It's a pleasure to give you an idea of what we are doing in this field of display, emerging displays, and the research being done on these novel displays. So as a first step, I would like to briefly introduce our company. We're in Winterthur near Zurich. I founded this company almost 20 years ago. And over the years, we have developed a range of R&D tools that are supporting industrial and academic research teams globally. So the first one is ZFOS simulation software, then LAOS simulation software for large area devices, and then 4 different R&D tools that can be used for research in displays or in PV research. So PV, photovoltaics, this is our second field, but the original field of activity is in displays where we still have, this is a very equally important market, PV and displays. So to give you an idea of 2 of the very well-known tools that we are selling, first of all, ZFOS that turned 20 years old last year, but just now, a week ago, we released a new version of this software with a new user interface. As you can see, the software has a light absorption, light emission solvers for display pixels. Then we also simulate the semiconductor charge transport of electrons and holes and recombination that leads to photons emitted. And then newly, we also introduced a thermal module that describes the self-heating of the display pixels that occurs if you drive a lot of current through the pixel. Then the software also includes optimization and fitting algorithms, which allows you to import measured data and extract material parameters like carrier mobility, but also optical parameters like refractive indices. The software runs on standard laptops and is therefore easily accessible. So the other product I have on this slide is PIOS, which is an all-in-one measurement equipment that simulates JV curves. Sorry, it measures JV curves. It also measures transient currents or transient light out from the devices, as well as impedance spectroscopy data. So that's frequency domain data. That's also a relevant property of these devices, and which reveals some device physics when you look closer into this kind of data set. Now, today I will speak more about simulation. So briefly, I will not talk about ZFOS, which actually is used for charge transport simulation and light out coupling, light in coupling, but I will give you an example of large area modeling software LAOS, which is this second one on the list here, which basically can deal with multiple pixels arranged in an array of pixels in a screen. And finally, this new product that we're releasing, it's a simulation software to evaluate the power consumption of a display for a given choice of subpixels and their properties of the subpixels. So let me start with a LAOS simulation study that we carried out, and the motivation fits well to this session today. It's about high-resolution displays. As you know, for VR displays, we prefer to have a really high pixel per inch density, and there we will actually running into some issues. And I'm mainly talking about OLED displays because this is the field we have most customers in. OLED displays for mobile devices, OLED TVs, and also micro OLED. These are the kind of customers that we have, and they use our tools. So they care about resolution, they care about high contrast, and they also care about color gamut of these displays. And one particular challenge, if you increase the pixel resolution that you encounter, is a crosstalk challenge. There can be 2 kinds of crosstalks. If, for instance, if you look at an RGB OLED display, that's a cross-section of side-by-side RGB pixels, which you would find in a Samsung display. There you typically have layers that are shared between neighboring pixels, and these layers can be highly conductive. For instance, a hole transport layer that is kind of bridging the neighboring pixels, and because of these neighboring pixels, I'm not sure if you can see my cursor. No. Yes.
Yes, we can.
Okay. So this there is some unwanted horizontal lateral leakage current happening if you have one pixel on, like here the blue one. You also end up having some light generated on the neighboring red pixel because of these shared layers of the two subpixels side by side. This is what we call electrical crosstalk. But then there's also another issue. If you make these pixel density higher, for the example of the white OLED plus color filter display approach that is promoted a lot by the LG display, which uses it for TVs, there you have an emissive plane of white OLEDs, which then emits light, and there is light leaking to a neighboring pixel through the color filter of the neighboring pixel, and that also can affect the quality of the image. So with our simulation software, you see on the bottom left, we published 2 papers already some years back where we started to study the electrical crosstalk happening in neighboring pixels, but we also did optical simulations for the optical crosstalk. And I'll show you this example here of a display where we actually, in the simulation, we just consider this lower right pixel being turned on, and then we have neighboring pixels which then would have color filters. So the one we turn on is the white pixel, and the neighboring colors, it's the green pixel, and the neighboring pixels can end up also emitting light. So in the study here, we varied the pixel definition. So that's the layer that defines the three-dimensional structure of an OLED pixel. So we varied the angle of this pixel definition layer from flat to very steep. And you notice here in some intermediate angle range, we do observe significant crosstalk here. If you evaluate the intensity map of light coming out, and at the bottom also the color that should be perceived by the viewer. So there's a parameter, the angle here of the pixel definition, but also the distance between the emissive plane and the color filter plane does play a significant role in this optical crosstalk. And what's happening here is just a sketch here. At intermediate angles here, there is light having a chance to also end up in the neighboring blue pixel, even if it was originating from the OLED below the green color filter. Now, we also combined a combined study where we looked at the electrical crosstalk on the upper left, as well as the optical crosstalk. So we do a 2-step simulation. In the first step, we evaluate the current density in the plane of the electrodes of this bottom white OLED array. And so we see these lower left pixels are turned on, and the other 3 around it, the white, the red, and the blue, are turned off. But nonetheless, there is some non-zero emission from the white pixel or also from the neighboring blue. And the overall effect that we get is actually depending on the current density that we're driving the display. And the OLED display industry has really looked into this and also found this to be detrimental, mainly at low brightness levels. So when you want to kind of have a pure color at low brightness level, you get a more disturbing effect of the crosstalk. As you can see, at 2.7 volts, you have significant contribution of the neighboring pixels. Whereas if you increase the voltage, this is not such a problem. But overall, the voltage-dependent color would then shift from yellow-green to the actually wanted green. So that was a nice study that we carried out and could be an example of what you can do with our simulation software and to tackle some issues in these high density developments. And it turns out that also nowadays manufacturers are also stacking OLEDs and introduce kind of a third layer, like a third electrode in between as charge generation layer, which is highly conductive, which again is going to cause problems with electrical leakage. Now, the second example I'm presenting today is about display power consumption, and this is very relevant for all mobile display applications like VR headsets, but also smartphones, of course. And there we always have a choice how to render the colors of the image that we want to display. And there are traditional ways. There is this way to just have side-by-side RGB, but there is also a possibility to stack the RGB on top of each other. Or there is a so-called turbo LED concept where you combine two different blues, sky blue and deep blue, and light red, deep red, light green, deep green, and to kind of play around with these display concepts, subpixel concepts. That's why we developed this software where you input current voltage and luminance curves, you input the primary colors of the subpixels, you input an image to be rendered, and for that given image, the software will calculate the power dissipation, power consumption that is resulting for that image. And then you can repeat the calculation for a different assumption of primary colors and then end up having a more optimized display subpixel set, which does not consume that much power and hence increase the lifetime of the battery that powers the mobile device. And here's an example of say an image. It's chosen from Swiss mountains. And you see the image has sky blue, it has snow, it has white snow, it has red flag, and so on. So the software, what we did here, we assumed this RGBW, so 4 subpixels that are for each pixel of the image, the display driver will select the most efficient combination in terms of the least power consumption. So for instance, if we want to render the grass here on the image, the green grass, it's actually sufficient to just take the white subpixel, the red one, and the green one, because the grass doesn't contain any blue. So, and this is advantageous because the white is actually a more efficient pixel than the other ones, because the other ones are color filtered pixels. So you see then the software puts out a map of those pixels for each triple of subpixels that is possible for these triple combinations. We get an image of the power and we get an overall image of the power consumption of the entire image. And we see, for instance, that the white snow and the red flag and the blue flowers consume the most power, namely because the deep colors are usually less efficient and then also drawing more power. And yeah, to quantify a comparison of different subpixel concepts, we just have seen on the previous slide the RGBW concept. And we compare it here to the traditional RGB, which has the disadvantage of you're using subpixels that are pure colors and that usually are subpixels with not as efficient electrical properties. And you see here the total image that was calculated here. The power consumption can be reduced significantly if we go from the traditional RGB to a RGBW display concept. And finally, as a quick outlook, our customers, they deal either with OLED stacks where they have to optimize layer thicknesses and care about charge transport, charge recombination, and so on, but also on thin film optics. Then we have this display. So as I've shown before with the crosstalk study, I've presented an example of a crosstalk issue in high resolution display. And finally, also the power consumption aspect that we address with OPIX. But a lot of players in the display community, they also go into optical sensing integration. It was mentioned earlier today that you can have eye tracking in VR displays, and that requires to have bidirectional devices that not only emit light, but also detect light. And that's actually shown here on the right. In addition to the RGB pixels, you also can integrate organic photodiodes, which in the cross section here, you see that they are very similarly, they are a sandwich of layers between anode cathode, and they even use similar transport layers, Hall transport and electron transport layers, and they would then absorb or reabsorb the light that is emitted by the emissive pixel in order to sense the reflected light from a finger, or maybe a reflected or an image that is projected from the eye that is being tracked, for instance. And a nice study has been presented this year by the Samsung Group research group. They have published this Nature paper where they also discuss the challenges that are involved, namely the electrical crosstalk issue, which is exactly the same thing as I presented before. Namely, if you have emissive pixels and also a neighboring OLED photodiode pixel, then you do have the electrical leakage among the emissive pixels, but also electrical leakage among the emissive and the neighboring light absorbing photodiode. And one way they try to overcome this issue is by simply introducing some ridges, some barriers for the charge transport to kind of lengthen the charge path by overcoming this, making this charge transport distance effectively larger by introducing this ridge. So they managed to do that and also quantify that. And in terms of optical leakage, it's a similar problem that not only do you get the light that you want from the actual finger or the object that should reflect the light, but also the photodiodes will also absorb the light that comes from neighboring pixel directly, and that's the optical leakage, which they also discuss here and try to circumvent by an ASP method, which is simply a word saying advanced signal processing, but not more details disclosed here. But yeah, that gives you an idea of the challenges that display companies have in doing advanced displays that even include sensing. With this, I'm concluding and would like to thank you for your attention. And I'll show you the team behind Fluxim. We have almost 40 staff members that develop and tools and support the customers. And if you have any questions about our product range, please get in touch. Thank you for your attention.
Thank you very much, Beat, for this nice overview and presentation. So we can take one question if we have for Beat. And if we don't have anything, I would like to end this meeting, and thanks all of our speakers today for their nice, inputs for these interesting topics of display for VR application. And yeah, thank you for attending this event. If you want to be in touch again with one of the speakers today, feel free to drop me an email. I will be very pleased to make the introduction. So thank you very much again. And just a reminder for you, we will organize next year, so next October 2026, an in-person meeting, not online, but this time in-person meeting at Luxottica in Milan, Italy. And we'll talk about augmented reality topics, but also display technology as well. So it will be one of our topics. So if you are interested in this event, feel free to check our website. And yeah, we can discuss this together if needed. So thank you very much again. And yeah, see you to another of our